Welcome to Saturday Morning Astrophysics at Purdue. I'm Yuthika Savant. I will be hosting today's session. I'm a sophomore here at Purdue. I'm majoring in applied physics. I'm also minoring in material sciences. I'm originally from Mumbai, India, and now I live in Columbus, Indiana with my family. Today's topic is going to be about black holes and gravitational waves, so it's going to be super, super exciting and extra special. Professor Dimitrios, I will let you get started.
Hello, everybody. I'm very excited to be here to be discussing about the general theory of relativity. It's a theory very close to my heart, so and I'm excited to have you here to discuss it. So a few things about me. I was not born a professor. I was not born an astrophysicist. Actually, I was about your age, 15 or so, when I was infected by a bug of curiosity. I wanted to learn more about the universe, about black holes, and about actually how things work around us. I soon realized that you need a good background in physics. So I did apply and I was admitted in a physics department in Greece. Where you get your good basis in physics and then you can apply this physics to the universe, to astrophysics. I continued with my doctor thesis in astrophysics, again in Greece, quite some time ago, and then moved abroad to Munich and to Princeton, where I was a researcher doing postdoctoral research, learning more about black holes, explosions in the universe. And then I was ready finally in 2012 to join the faculty at Purdue. It has been a long trip, but it's also an amazing trip exploring all these mysteries of the universe. And with me today here is also my graduate student, Foison, who may want also to say a few things to you about himself. He will be helping me making demonstrations of how two stars come together and collide.
Yeah, thank you, Professor Dimitrios. Hello, everyone. My name is Zhaofeng Wu, but just feel free to call me Foison. And I'm a PhD student here at Purdue working with Professor Dimitrios. And I got into astronomy ever since I was a kid, and because I was fascinated about the planets and, of course, the idea of aliens. But when I went through my undergrad as a physics student, I found something even cooler, the black holes. And they're so interesting that it keeps me wondering why these kind of strange things happens in nature. And finally, I started researching them. And this eventually led me here working with Professor Dimitrios. And also, I really love stargazing, but I was grew up close to Hong Kong, where the light pollution is very strong. So usually you can only see the moon and also the Jupiter. And coming to here at Purdue is very amazing because the night sky here is much darker. And I finally have the chance to see so many skies on the sky, so many stars on the sky. And Purdue also have one of the best astrophysical programs, and the vibe here at the department is very relaxing. So if you want to study astrophysics, I think Purdue is a very good place for you. And I'll send it back to Professor Dimitrios.
Since we have here the first slide of my presentation, and you also may have noticed an image I have there. And the topic of this presentation is the general theory of relativity. Who can tell me what we are looking at this image? Can you give it a try? What is in the background and what is in front and what happens in this image?
It's a black hole trying to bend the space and light through the event horizon. Okay,
so you see a black round thing. That's quite correct. Okay, maybe we ask you to give the lecture here. So it's a black hole. So what is in the background? Can you see?
Like a bridge?
Yeah, it's a bridge, and the background is the picture of a bridge, and there are cool software programs that take this picture, interfere the gravity or mimic the gravity of a black hole, and see how things are getting distorted because the light passes through the black hole. And actually, it's one of the amazing predictions of general theory of relativity, that light that passes close to gravitating masses bends, and then you get effects similar to what you get with a lens, when you have, for example, a lens distorting an image. So let's explore all these things together. Now, the story starts around the 1600s, like 300-400 years ago, when Newton came up with a description of how gravity works. He described gravity in terms of what? In terms of forces. An apple fell on his head, that's at least the story, and inspired him to write down the attraction, the global force, the description of the global force of gravity. Can anybody tell me what determines the strength of gravity between two masses?
Distance?
The distance, right? How far or close. So what happens when the two masses are getting closer together? What happens to the force of gravity?
Gets stronger.
Correct. There is this term in the denominator, r squared. This is the distance. As if you halve the distance between two objects, the force becomes 4 times larger. Of course, the force of gravity depends on how big the masses are, right? And that also means that if we increase the masses, then the force of gravity gets stronger. With this law, Newton was able to describe how planets revolve around the sun, but also how an apple falls on the Earth. The same laws of physics apply on Earth, but also everywhere in the universe. And it has been shown to be a very accurate description of nature for a long, long time. You could describe, for example, the orbits of the planets around the sun. What are these orbits, actually? How are the planets rotating or revolving, to be correct, around the sun?
Most of them are circular, but I think it's Pluto, and one other one is just like an oval or an egg.
Yeah, like elliptical.
That is elliptical. That is exactly correct. So most of them are almost circular, but in reality, they are following in general elliptical orbits, which means at some point they get a bit closer to the sun and further away at some other point of their orbit. Now, I run the clock now for a few centuries fast, and it was early 1900s where Einstein figured out how space and time work with the special theory of relativity. And in accordance to the same theory, he also 10 years later figured out how gravity works in this context of space and time. He described gravity not in terms of forces, but in terms of curved space and time. He figured out that when you put a mass, the space curves around this mass, and then all the other objects actually are moving on this curved space and time. Now you can imagine how a mass or an object would move when there is no other mass around it. In that case, the space and time are flat. And how would you imagine an object moves if there is nothing else around it?
In a circle around the edge of the curve. Oh, if it's flat, then it just moves straight. No.
Straight line, right? If the objects are lazy, if they don't move, they stay where they are. If you give them a kick and move with some speed, they keep moving with the same speed forever. So in a flat space and time, if there are no other masses, you have straight line. This is the orbit. However, if you bend space and time because you have a mass, then the trajectories are different, and they look a lot like what Newton described. But let's make an experiment. I'll show you now a video where I try to mimic this effect of curvature of space and time through having an elastic membrane. As elastic sheet, I put a mass in the center, some weights, so you can see here what we're having. Stretch sheet, I put these weights in the center to curve the sheet, and I will be rolling balls around it. So let's see what is happening. Or what do you expect actually to happen? Who can tell me what do you expect will happen if I try to throw balls around this center?
Well, as the mass isn't that big, like the trajectory would be like curved.
Right. I'll roll them and they will start having curved trajectories. Let's try to see what type of trajectories we get in this example. I roll one ball and, well, makes a nice circle. I roll another one. Notice, what do you notice? The ball that is close to the center rotates slower or faster?
Faster.
Faster. The balls that are far away rotate slowly. Now you can have the balls having elliptical trajectories or quasi-spherical trajectories. And that is mimicking the effect of general relativity. Space is curved and objects are moving on this curved space. It mimics the trajectory, for example, of planets around the sun. Does it make sense to you? Do you have any questions on this demonstration? Well, let's move on. Now, we have a new theory that describes space and time and gravity. What should we do with this? What do scientists do when a new theory is proposed?
Test
What
it.
do you think? Excuse me?
You test it.
You test it. Of course you test it.
Professor?
Yes.
Professor?
Yes, correct. Tell me.
Can you hear me okay?
Yes, yes.
Could I ask just one question? I want to go back to this model that you just did. So I see these smaller masses circling around either the same direction or opposite direction around the center mass. So I'm interested in asking, is the effect of the center mass on the smaller objects related to the effect of the smaller objects on the center mass? In other words, is it a reciprocal interaction?
That is correct. In reality, everything attracts everything else. And even the small masses are curving space and affect how the big mass is moving. In this demonstration here, because you set the big mass to settle in the bottom and to bend, there is friction and you don't see this motion of the big mass. But in reality, both masses rotate around the center of mass. Everybody affects everybody else. Of course, little Earth doesn't do much on the sun, but the sun is having 1 million times more mass than the Earth is dominating the Earth's trajectory. Now, when we have a new theory, indeed, we test it, we question it, and we interrogate it, and we try to prove it actually wrong. That's the challenge of the physicists, to question everything. And indeed, the theory made some specific predictions. The theory of general relativity made some specific predictions that could be tested. Now, as we said, according to Newtonian gravity, the planets move on elliptical orbits, and the axis of these ellipses is constant, doesn't change with time. That means that the closest approach of the planet to the star, it's always at the same point. However, scientists had noticed already 100 years ago that Mercury is misbehaving. Its closer approach, the perihelion, is shifting tiny bit with time. They couldn't explain it with the gravity of Newton. In fact, general theory of relativity predicts this precession of the axis. It's this here you see this effect exaggerated, how the ellipse is shifting, rotating around. And they could measure this precession. It's exactly agreeing with the predictions of general relativity. That was the first strong evidence that this is the most correct description of how gravity behaves. Moreover, the general theory of relativity makes another amazing prediction that light trajectory bend when they pass close to a gravitating source. Such bend happens even if light passes, say, close to the sun, and the bending is a tiny bit, but still can be measured. To do this measurement, however, you had to look at a source like a star when the light is very close to the sun. Of course, we cannot see the stars when they are very close to the sun. But there is an opportunity, and the opportunity is when there is a solar eclipse. So to measure this bending of light and to test the general theory of relativity, we had to go to wait for an eclipse, a solar eclipse. That happened over 100 years ago, a few years after the theory was proposed. Researchers had to go all the way down to the southern hemisphere in South Africa to make these measurements. There were very tricky conditions. There were some brave people who went down there and did very detailed measurements to measure this tiny shift of the location of stars because of the position of the sun bending the light from these stars. They could verify the predictions of theory to very high accuracy, and that actually convinced the physicists that the theory is correct. Now, if you have a theory that you think that is correct, what else you think you would do as a, who can tell me what else would you do with this theory?
You could test the limits of it.
You can test the limits. You push it to its limits. You try to break it. You are always challenging the theory. You push the limits. You try to make new predictions about things we haven't seen. And if you think about limits and predictions, the people started thinking, how about very strong gravity? How strong can gravity get? Let's put a lot of mass and squeeze it together in very little space. What do you think happens in that case?
Space just breaks.
Space bends, and the more you concentrate the mass, the space bends more and more. And in some sense, yeah, you are right. Space breaks. Everything collapses in a single point, and then you have a black hole. You get a surface from which not even light can escape. That is called the event of horizon. And all the mass is concentrated in one point. Since not even light can escape from this object, you call it a black hole. Now, these objects are tiny. The size of the horizon for a black hole that has the mass of the sun is tiny. It's actually 3 kilometers. It's more or less your commute to your school. That's the distance of the size of the horizon if you take the mass of the sun and collapse this mass to a point. It's a tiny object. And that's an amazing prediction of the theory, that you can break space and time and you can make these amazing objects. This prediction was realized almost 100 years ago. But that's not the only amazing prediction that the theory makes. Another is that there are gravitational waves. When two big masses rotate around each other at high speed, then they make ripples of space and time. These ripples propagate throughout the universe with the speed of light, and that results in this orbit of the two masses to lose energy. The objects come closer and closer together, and they collide. And in fact, I think this is a good point for Foison to give us an optical demonstration of how this merging can take place.
Yeah. So Dave, could you keep? Yeah, here like a try this one.
Okay, I'll come in and give a hand, and hopefully I won't mess up your demonstration.
No.
Okay, so what do we have here?
Yeah, so we have two boards here. You can see it attached to two strings, and here's a bar that's attached to string. And let's try to.
So what this is a like a metal metal weight. Okay, so that's eventually going to slide down the strings, right?
Yeah, this will like demonstrate the optical length, because like if it's smaller than the optical length, then the orbital length is very small, but when it's like
Okay.
up here.
So we're going to start these. What are these, black holes?
Black holes or neutron star, whatever.
Black holes or neutron stars. We're going to set them in motion and see what happens over time. Are you ready?
Yeah.
Okay.
Yeah.
Here's the mass.
Yeah.
And bam!
Yeah, so students, it's like any thoughts about what is going on this kind of demonstration?
If you were detecting the gravitational waves, then like you'd see some activity and then it would spike and then go silent.
Okay,
You
yeah,
see
you're very.
it starts to like have some waves and then a lot of waves and then a massive wave because of the explosion, and then it's just back to normal.
Yeah, good. And I think one of the, so Naomi, you're raising your hand. You can also go ahead.
Yes, well, it appears that since gravity increases with closer distance, then it's the closer they get, then looks like the faster they're spinning, so stronger gravitational pull between them is getting.
Yeah, you're quite like catching up the point. So you can always like see like when the two boards are closer to each other, the speed they're moving is faster. Yeah, this is like a very good insight. And that's because, of course, the gravity is stronger when two object is like closer. And actually, you're also correct that the gravitational wave, when it's closer, is also emitting stronger gravitational wave of the system. And do you have any other response to this demonstration? Yeah, no, like, what about Dimitrios? Do you have anything to add?
No, thank you for
Sorry,
thank you. Yeah.
I have a question. So,
yeah,
well, this situation still can happen in the water, right?
happening in the water. Yeah, if doing in the water,
it's the same. Yeah, okay, you got me.
Yeah, you can see the ripples. That is the gravitational wave if
Yeah.
we in water. Yeah, but unfortunately, water is very hard to prepare and can split over and then mess up everything. So better
And
keep
also like a tornado. I'm not sure my pronounce is corrected.
Oh, tornado. Yeah, tornado is like some kind of a similar thing, but tornado is the ripple in the air. But here, so one of the cool thing about gravitational wave is like what is the ripple? What is it affecting? It's not like air or water. That's like a medium. It's the space and time itself.
Okay.
Yeah, it's stretching the space and time accordingly. So in principle, there's no medium, or the medium is the space and time. So that's a really amazing thing. Yeah. So yeah, send it back to Dimitri.
So thank you, Faison. And from the questions I get that, I think that I could get the students to give this presentation because in fact, yes, there is close analogy between ocean waves and gravitational waves. You see some ripples propagating now on the surface of a lake or something. And the gravitational waves is something similar, but there is no medium. They propagate in space and time. They can propagate in a vacuum. That's one of the amazing predictions of the theory. In fact, the gravitational waves, they are not limited to black holes or neutron stars. When I put my hands around each other and do this, I produce gravitational waves, but don't try to measure them. They're extremely, extremely weak. There are gravitational waves produced because the Earth rotates around the sun. Again, they are so weak that it's hopeless to try to measure these waves. It takes big objects rotating really fast. And in that case, black holes or neutron stars, these extreme objects, are the best sources when you want to hope to measure these waves. Now, it turns out that black holes are all around us in the universe. In the last 50 years or so, we have discovered millions of black holes. At the centers of galaxies, there are huge black holes, and each galaxy has millions of black holes of smaller mass that come from the collapse of massive stars. So I want you to take you a trip to see where some of these big monsters are lying. Who can tell me, what are we looking here in this picture? It's something of it's a picture of the night sky, but if you notice something particular about this picture.
The Milky Way.
Well, that's exact. It's the Milky Way. Can you see there's a stripe of brighter light? If you are in a very dark place, and there are not many dark places, unfortunately, around here. But anyway, if you go in a very dark night and clear night, you will see a white stripe of light. And what is this? The Milky Way. It's our own galaxy, right? It's all the stars in our galaxy that appear like a straight line in the night sky, because we live in a disk galaxy. Okay, now I want to take you a trip from the southern hemisphere, where? To the center of our galaxy. People have looked with ever better telescopes to resolve to see what happens exactly at the center of the galaxy. So it will be like a trip where you are zooming in this direction. So let's watch this video and see what is happening. We're somewhere in the southern hemisphere, and now you can see the big picture of the Milky Way. And we start approaching it with some dramatic music. That's important. So all these points, what are these? These dots are all stars. And there is gas, and there are black holes, and clouds. But we keep zooming in something that is not very spectacular, at the very heart of our galaxy. And these dots become bigger. We see distant stars that they are thousands of light years away at the heart of our galaxy. And here, with the best technology we have, we could follow the motion of stars very, very close at the very center. So what do you see here? What do you see these lights doing?
Orbiting and revolving around each other.
They're revolving, they're moving around. Look at this trajectory here. One of the stars rotates, it's called S2 star, rotates around an invisible center, has an elliptical orbit, and turns around. In fact, we have seen many of such stars. Now we are zooming out a bit to see a dozen of these bright stars at the center of the galaxy. They are all rotating around, revolving around an invisible center. Their trajectories are perfect ellipses. These orbits can take decades to be performed. It took researchers a long time to see this motion, to study the motion of these stars.
Professor, we have a question in the chat.
Sure.
What about the dark spots? Is it just space?
Yeah. Space is dark. There is no light. What we can see with these telescopes is the little points, which are stars. But when we saw the Milky Way, I think I understand the question. When we see the Milky Way, we also saw some dark lines. And that's actually dust. Dust and clouds are blocking the light. So in some directions, there is all this dust that is essentially blocking the light. You cannot see it with the light we see with our eyes. You have to look at the infrared. Dust produces light at different wavelengths. That's a very good question. And I believe we have one more question. Or not really. I see some questions in the chat.
We have a new question now. How far from the center of the galaxy are we?
We are 30,000 light years. So that means for light, it takes 30,000 years to make it from the center of the galaxy to us. That's a huge distance. And these stars are away from this center, from this black hole, at a distance that's comparable to astronomical unit, to the more or less to the distance from the sun to the earth. These are tiny distances. We are looking at a very busy spot in the center of the galaxy, and we are looking at individual stars moving around this center. This is another movie of how the stars move around. The star in the center denotes the black hole, the location of the black hole. Now, when you can measure the period of the revolution of the stars, you can also measure how big is the black hole. And the outcome is amazing. This is a monster there. It has mass 4 million times larger than the sun. You put 4 million suns together in a black hole and forces all these stars to revolve around it in this violent way, to revolve around it very fast. Do you have questions on this?
If this is the center of our galaxy, could there be like another like smaller with a smaller mass, like a black hole somewhere else inside the galaxy, but still rotating around the big black hole?
That is a good question. And yes, in fact, we know that in our galaxy, we have seen 20, 30 different black holes that are much, much smaller. Their masses are typically 10 times the mass of the sun, and they revolve together with the rest of the stars around the center of the galaxy. We have seen only 20, 30, but our models predict that there are millions of them. We just don't see them because they are dark. You need to have something to revolve around the black hole to be able to spot the black hole. The black hole on its own is dark and hard to spot. But that's an excellent question. Black holes are all around the place.
Yeah, another question. What creates black holes?
These black holes I'm talking about, the smaller ones, come after big stars die. You have heard about supernovae and explosions. Yes, when the stars live their life, the big ones explode and give you supernovae. Actually, even bigger stars don't explode at all. When they live their life, they cannot burn any more nuclear fuel. They collapse because of their own gravity, and they form these black holes. We estimate that we have around 100 million black holes in our own galaxy alone.
I think I just heard you say like that's for the small ones. What about
Yes.
like the really, really big ones?
I don't know. Okay, we see that every galaxy has a huge black hole at the center. These black holes form early and evolve together with the galaxies. They grow together. They feed on each other. The black hole feeds on the galaxy. But how exactly these monsters formed so early and they grew so big, we really don't know. We have theories, we have models, but we really don't quite understand it. But observationally, we know that practically every galaxy has a huge black hole at the very heart of it. They sink in the center of the gravitational potential, and they are fed constantly gas from the galaxy. I have another question.
Yeah, also Nathan like raised his hand, so maybe do you have anything to ask?
Do we have any like proof of a primordial black hole, like a black hole star?
Well, that's the other big question. Are there primordial black holes? These are black holes that have been speculated to be forming very early in the universe, just after the Big Bang. And there are many theories that predict such smaller black holes that fill the whole space. We haven't discovered any of this so far. We keep looking with different methods. Theory predicts them, but we don't have any evidence. We haven't seen them. But that's for the young generation to discover.
Yeah, and also we have one more question in the chat. Does everything in the galaxy orbits the black hole?
There is this huge black hole at the center, and yes, in some sense, everything in the galaxy rotates around that black hole. But keep in mind that the mass of the galaxy is much larger than the mass of that black hole. So in that sense, really, everything revolves around everything else. So our sun revolves around the center of the galaxy, but it sees effectively a much bigger mass than these 4 million solar masses. The mass of the galaxy is actually 1,000 times larger than that. It's billions of times the mass of the sun. So the black hole controls the motion of the stars very close to the center, just like we saw in this video here. It doesn't control exactly the motion of the stars further away, like the revolution of the sun around the center of the galaxy. That's because of all the masses that are in the galaxy. That's excellent. We have a very nice discussion. We can keep going on black holes forever. I don't mind. Are there any
more questions?
There are more questions coming out. Yeah. So there's one question about, do all galaxies have black holes in the center, or is it only some of them have it, like this big monster?
Well, we are not sure for every single galaxy, but in all galaxies that we have good data and good observations, we find black holes. So the current understanding is that at least most of them have, and maybe all of them. Again, we don't understand how they formed and why they are there.
Still an open question. And there's also one more. Do galaxies themselves orbit around more black holes? Like if we have like several black holes in one galaxy, for example, is that a case for?
That is such a good question. In fact, galaxies are not isolated islands of matter. Galaxies can start colliding with each other as they move in space. That's the merger of galaxies. And after the galaxies collide, in fact, the black holes that they have in their center can come together in the center of this train wreck, of this crushed new galaxy, and they form a binary of two supermassive black holes that eventually collide with each other. So as galaxies collide, supermassive black holes are expected to collide as well and produce gravitational waves. I'll continue a bit, but I'm very excited to answer your questions. Just to say that these amazing observers that did these observations got the Nobel Prize of Physics 4 years ago in 2020. That was amazing and very detailed work. But these observations didn't actually show us the black hole itself, show us the effect of the black hole on the trajectory of the stars. Can we hope to see a black hole? Well, black holes are very small objects, and they are very far away. So they appear tiny on the sky, right? But what do you think? Can we see at all a black hole?
Well, you should see the light like entering the black hole, so it creates like a really bright ring.
Right. So if a black hole is alone, it's something dark you don't see. But if there is light, or if there is gas, hot gas falling into this black hole, then it shines. And when the gas shines, you can look at it, you can observe it. Well, the point is now that the black holes are so tiny to be able to see the silhouette, to see this dark spot surrounded by some light is extremely hard. Okay, they are tiny objects in the night sky. Even the larger black holes, like the one in the center of our galaxy, they're still fairly small. It's tiny. And let's try to give it a guess. What is the size of a black hole in the night sky. And let's compare it with a dime. Let's take a coin and try to hold it far away from us and see how far away from us should we bring this coin so that it looks like a big black hole in the night sky. Okay, so we have our coin here. And my question is, okay, how far should I hold this coin so that it has the size of a black hole as seen by us observers in the night sky? Is this question clear actually, or you want me to repeat it?
So a student asked, what is the difference between dark matter and black holes if are only detectable by how they affect things around them?
I will come to this. Okay, just to say briefly that black holes are very concentrated because of their gravity, while in general, dark matter doesn't produce light, but is believed to be more spread everywhere. So their effect is harder to detect. The spread on distance is even bigger than the size of the galaxy, while the black holes are very concentrated. So that's why it's easier to detect a black hole than dark matter. But let's see. Do you have a question? Did you understand the question here?
Some of the students already give the answer, but
okay. So who can give me a guess? How far away should I keep this dime to appear like a black hole in the night sky?
On the moon?
On the moon. We want to take it all the way to the moon. Why would you say that?
Because if you see like the size of many things, like many of the objects we see in the night sky, they're actually like a fraction of a degree in the night sky. So you would feel like something that it's like that far apart and like that far away should be really, really small.
Yeah, you say black hole is such a tiny object and the distances in space are so huge. So of course it looks something tiny. Well, in fact, you got it right with the first try. It's like putting a coin on the moon. Let's throw a coin on the moon. That is the size of these black holes. These are so tiny objects in the night sky that would appear that it's completely hopeless to try to detect them. In fact, scientists, again, brave observers, managed to put a program together to see the silhouette of a black hole at the center of another galaxy, not our own galaxy. They started with another galaxy. They zoomed in with the best telescopes in radio wavelengths, in smaller and smaller distances, scales at the center of that galaxy. And finally, in 2019, they published their amazing results. They found a bright circle of light that is really the horizon, the size of the black hole at the center of that galaxy. That black hole is absolutely a monster. Its mass is 6 billion times the mass of the sun. It's so big that we could marginally, with the best technology we have, see this. In fact, you had to put telescopes everywhere on Earth, look at the same time at the source, and use interferometry and special techniques to try to resolve. You used the whole of Earth as a huge telescope, essentially, to look at this source, and you could marginally take a picture with the best technology of this black hole. And the picture is exactly what you would expect from the general theory of relativity. So now we have not only detected the effect of black holes, but we have literally seen a black hole. More or less, this dark circle in the center is the black hole. It has the size of the horizon of the black hole. Do you have questions on this?
Yes, I do. Why did they take the picture of like of a black hole in another galaxy and not our own?
That's a good question. It just happens actually that both of these black holes have the same size on the sky. The big black hole at the center of our galaxy is actually 2,000 times smaller in size, but is also 2,000 times closer to us. So in the night sky, it appears to have very similar size to that huge black hole in the faraway galaxy. The difference is that this source, this black hole, doesn't change with time. Its brightness remains the same. So you can observe it with your telescope for longer time, add up the light, and you can get a more crispy image. They try to do exactly the same thing with the black hole in our own galaxy, and the images are more blurred. They are more shaky. So it's harder to detect our own black hole. It was easier to get the first silhouette of a black hole from that galaxy. But it's an excellent question. Now, I don't want to keep you for too long, so I just want briefly to discuss another revolution that happened in this field a few years ago and has to do with the detection of the other extraordinary prediction of Einstein's relativity of gravitational waves, these ripples of space and time. Now, to detect these waves, actually, even when you get two black holes coming and colliding together, it's extremely hard. You have to measure distances, to measure these tiny distortions of space and time that can be essentially measuring the distance to the nearest star with the accuracy of the thickness of the human hair. That is the type of distortions we are talking about. Again, I would naively say that's hopeless, let's forget about it. But there were brave people, crazy people that said in the 70s, no, let's do it, we can do it. So for 40, 50 years, they set up lasers, interferometric structures, shooting lasers in mirrors, trying to make a very stable measurement of the distances to try to find gravitational waves passing through our sources. This experiment took decades to be completed. It happened in the US in 2 locations, in Italy. It's a big collaboration. And I have a short video, but I will not play it in the interest of time. I will just tell you that there was this amazing discovery that happened, announced 9 years ago, of detection of gravitational waves from collisions of black holes. The signal is exactly what our friend here described before, about two black holes coming closer and closer together. The frequency started increasing, and poof, the two black holes collided and the signal disappeared. We have seen this signal since then about 100 times. 100 different pairs of black holes have collided and have detected this signal in gravitational waves. Now, when two black holes come and collide, you only get gravitational waves. And that's such an amazing, of course, discovery. And yes, sure enough, it gave a Nobel Prize in physics. That happened in 2017, given, of course, to these brave people that did these measurements. Now, we can get gravitational waves also from the collision of neutron stars. And the difference to black holes is that neutron stars have matter that is not hidden behind the horizon. And when two neutron stars collide, you get light. So that's an animation of how the collision of two neutron stars can look like. And you see now that it's an extended object and you shred gas. And eventually, after the two neutron stars collide, you form a black hole. But you still have a lot of hot gas around and you can get fireworks. You can get light out of this explosion. And actually, this light is beamed and it can give you a bright flash of gamma rays. Or that was speculated for some time. Now, I'm saying all of this, of course, because such detection did happen several years ago. 7 years ago, with gravitational waves, we saw the gravitational wave signal of two neutron stars coming together, colliding, and then 2 seconds later, we saw the light from this collision. But now we can convert this signal from gravitational waves to audible. We translate the frequency to frequencies we can hear with our ears. So let's actually hear this collision of two neutron stars.
I can. Okay.
Yeah, it's only here the very end, in the very end, I think.
Okay, so there is some filter. So the signal goes like. Okay.
Maybe you can run again to see like or tune up the volume a little bit too for the students to hear about it.
I'll try my best.
Yeah. Yeah.
Okay, it's the frequency. The frequency increases with time. The signal gets stronger as the two neutron stars come closer and closer together. This is played in real time as the observation happened. And then the signal disappears. And 2 seconds later, this thing is actually gamma rays. We got another signal that was light that came from the same position in the sky. It was the light that was produced after the collision of the two neutron stars. This is, of course, very exciting discovery. We got a lot of light. We studied this light. It's still observed today, 7 years after the explosion. And we learn a lot about what happens in these collisions. For example, we learned that there is a lot of metals, heavy metals and heavy elements that were created in these collisions. A lot of gold, a lot of uranium, a lot of platinum that is forming. So the heaviest elements we have on Earth, we believe now that they form in the collisions of two neutron stars, and this is a material that is spread around after these collisions take place. Now, I'll finish here. I'm just going to say that that's a brand new field of research. There is much more to be discovered. Mergers of supermassive black holes have not been discovered. We need different telescopes for this in space. We have seen two black holes colliding. We have seen two neutron stars colliding. Any guess what else we could observe? Who can tell me what else we could hope to observe with these gravitational wave telescopes? Well, we got two black holes, we get two neutron stars. The next thing you could imagine that we could detect out there is what?
A black hole and a neutron star?
A black hole and a neutron star, and that's exactly what we detected a few months ago. It was a neutron star, it was a black hole, it was a neutron star 1.5 times the mass of the sun. It was a bigger black hole, 10 times the mass of the sun. They came together, they collided and produced gravitational waves. That's just to tell you, it's a brand new field of research. There is a lot of discovery. And yes, we just wait for the young generation to take over and make all these great discoveries. I'll stop here. I want to leave some time for discussion and to answer any questions. But thank you for your attention. Maybe, yeah, I give it back to Utica.
I was also going to ask who has a question for Professor Giannios or Foizon or any of the TAs. We've been getting great questions throughout the session, and now's your chance to ask even more.
Do gravitational waves like physically affect anything like on Earth?
Yes, actually, gravitational waves are as real as anything. If you are, of course, on Earth, it's such tiny the effect. It takes the most sensitive instruments, and then it's tiny the effect. But you can imagine yourself in a spaceship witnessing the collision of two black holes, and then really your shape will be deformed by the passage of gravitational waves. You will be stretched and squeezed at the frequency of the gravitational waves. If you are too close to a black hole, the tidal forces of gravitational waves can literally rip us apart.
Kind of building off of that question, we can conclude that the interactions between neutron stars, black holes, produce stronger gravitational waves than, say, the Earth orbiting the sun, or as you were doing, moving your arms like this. What exactly dampens the energy of these waves so that when they reach Earth, it doesn't cause basically that deformation?
Yeah, so it's like everything. Any source that is far away, it faints with distance. So the fact that they're happening so far away means that as the waves expand, they get weaker with distance. They carry the same amount of energy, but over a larger area. So it's essentially, it's like the sun. If you go away from a star, it looks fainter, so it doesn't burn you. If you are at the surface of the sun, you are toasted. Here on Earth, we enjoy it. At the Mars distance, it's not enough. So it's really the distance that dampens it. How strong the waves are depends on the masses and on their, essentially on their acceleration, on their velocities. So you need masses that are very big and that they move with a speed close to the speed of light to make very strong waves.
It's not strictly related to the topic, but in the beginning, Professor mentioned that when he was like choosing his undergraduate degree, he like decided on physics because he thought astrophysicists should have like a really good physics base. Now, if I'm thinking about studying astrophysics or I want to get to that field of study, then would you recommend to do the same, or do you know any other paths to get to astrophysics?
That's a good question, a very practical one. There are a lot of very good astrophysics programs, which will give you good knowledge of physics and a more applicable knowledge in astrophysics. That's another very valid path you can follow. If you have a strong preference for theoretical astrophysics, I would advise that you start with a very good study in physics, in a physics program, and then you can always learn the astrophysical objects and the astrophysical details. But if you have, if for example, you want to be experimentalist or observing astrophysical sources, you can go either way. You can be with a physics degree or directly with an astrophysics degree. That's my general advice. They're both valid paths.
Thank you.
Sure.
I'd like to thank Professor Giannios and Farzan for this wonderful session that they had for us. It was very fun. I had fun and I learned a lot of things today. I just want to end the session by thanking Professor Giannios once again and Farzan for this awesome lecture that you guys had. And thank you, the TAs, for being here and answering questions. Thank you, you all students, for attending this session. And this would not be possible without you. So stay tuned for the next SMAP, and we'll see you there. Have a good day.
Bye-bye.
Bye-bye. Have a good day.